Hello and welcome to lesson number 34, Complex Numbers Part 4. This is going to be my last video on complex numbers. If you're interested in watching my other 3 videos on complex numbers, then check the links in the top right and in the description. Lesson number 34 is going to be on a single theorem with a notoriously difficult name to pronounce. In fact, this name is so difficult to pronounce that our own teacher's guide has actually gotten it wrong and misspelled this theorem in their lesson. As you can see here, they have misspelled it as DEMOVIER''S. This, if pronounced, would be pronounced as Demovier. This is not the correct pronunciation or spelling of this theorem. The correct spelling is this spelling right here, which is DEMOIVRES, which if you pronounce it, and I apologize if I pronounce this incorrectly, would be pronounced as De Moi Vr, which if you put it together would be Demoir. So therefore, this is Demoir's theorem. Now, considering Demoir's theorem states that if you have a complex number z, which is of the form z equals r times cosine theta plus I sine theta, where r and theta are elements of the real numbers, and you have some value n, which is also an element of the real number, then if you take z, which is the complex number of this form, to the power of n, then the result you're going to get is going to be r to the power of n multiplied by cosine of n times theta plus I sine of n times theta. So you can see here the radius or the size of the complex number or the modulus got increased to the power of n. However, the angle on the inside became n times the original angle. As you can see here, we have r and we have theta, which became r to the power of n and n times theta. So if you think about it, what happened here is that the complex number got rotated around the axis. It got rotated such that its angle is now n times the original angle, and now its length is r to the power of n, where r was the original length of the complex number. Now, it is important to note that if n is not an element of the integers, then there can be other solutions than the one found above. So this thing right here, Demoir's theorem, is going to give us only one solution. However, if n is not an element of the integers, then there can be other solutions. For example, if you take the square root of a number, as we know, there are going to be 2 solutions. If you take the cube root, there are going to be 3 solutions, and so on. So because of this, Demoir's theorem is only going to give us one solution, and we have to remember that it's only going to give us one solution. Well, remember that there are other solutions that we could get which are different from the first solution. Now, this is not going to be a problem if n is an element of integers, since the solution we get is going to be the only one. However, if n is equal to half or a third or something like that, or maybe some irrational power, then we could get more than one solution, in which case Demoir's theorem is only going to give us one of them, and we have to go to the others based on the rules of multiplication and addition. Now, moving on from that, what we're going to do next is to prove Demoir's theorem using induction, but we're only going to prove it for the integers, and after that, we're going to take a look at some examples of where we could use Demoir's theorem. Now, to start off with proving Demoir's theorem, what we're going to do is to let z be a complex number which is of the form r times cosine theta plus I sine theta, since that is where Demoir's theorem starts. So we're going to say r and theta are elements of the real numbers. Now, let's consider multiplying z by itself. So as we know, if you have, let's say, z1 equals r1 times cosine theta 1 plus I sine theta 1, and you have z2 being equal to r2 times cosine of theta 2 plus I sine of theta 2. Given this, as we found in the previous video, when you multiply z1 and z2, z1 times z2 is going to be equal to r1 times r2, which is going to be the common radius, times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. Now, according to this, if we substitute both z1 and z2 as z, then we can see z times z, z times z, or z squared is going to be equal to, and if we consider what we have, r1 and r2 are both equal to r, so therefore we have r squared here, we have r squared times, and then on the inside, cosine of theta 1 and theta 2 are both the same, so therefore we have cosine of theta plus theta, which is cosine of 2 theta, and therefore we have cosine of 2 theta plus I times, and then here also, since theta 1 and theta 2 are both equal to theta, we have the sine of theta plus theta, which is 2 theta. And therefore we can see for 2 over z squared, we're going to get r squared and cosine of 2 theta and I sine of 2 theta. Now we can see if we do this again, if we take z squared and we multiply by another z, then we're going to get this whole thing times another z, which is going to be r squared times r times, and then here we're going to have cosine of 2 theta plus I sine of 2 theta times, and then the other one which is going to be cosine of theta plus I sine of theta. And as we can see, this is again going to become r squared times r, which is r cubed, times, and then this thing is going to become cosine of 2 theta plus theta, which is 3 theta, and therefore we have cosine of 3 theta plus I sine of 2 theta times plus theta, which is going to be I sine of 3 theta. And therefore we can see, as we get bigger and bigger powers for the positive integers, we're going to end up with r to the power of n times cosine of n theta plus I sine of n theta. Now we could do this properly with induction, and if you want, I would recommend that you try it at least with the proper method of, taking the base case and then multiplying and then considering the n equals p case and n equals p plus 1 case, and you can do that. But for now, I'm just going to show you the pattern and stop there, and then consider it for the negative integers. So for negative integers, we have to start with 0 and then go down. So considering 0, z divided by z is equal to 1, provided of course that z is not equal to 0, and z divided by z equals 1 could be written as r to the power of 0 times the cosine of 0 times theta plus I sine of 0 times theta. Because if you consider this part here is going to be equal to 0, since 0 times theta is going to be equal to 0, and sine of 0 is going to be equal to 0, times I is still going to be 0, but for this part we have cosine of 0 times theta, which is going to be cosine of 0, which is going to be 1. So therefore we have 1 here, 1 plus 0, and over here r to the power of 0 is going to be equal to 1. So therefore we get 1 times 1, which is this thing right here, and we can see therefore it works for z to the power of 0. Now going one down, if we then divide by another z, we can do z to the power of 0, divide by z, which is going to be z to the power of 0 times z to the power of minus 1, and as we know, z to the power of minus 1 is going to give us, it's going to be equal to 1 times r to the power of minus 1 times, and the stuff on the inside is going to be cosine of negative theta plus I sine of negative theta, and continuously forward. So now we can see, if we keep doing this, we're going to eventually get r to the minus 2 times cosine of negative 2 theta and so on and so forth, and we can see that way also we're going to get cosine, or rather r to the power of n times cosine of n theta plus I sine n theta. So therefore, if you do this properly with induction, you're eventually going to get De Moivre's theorem for the integers. Now I'm not going to prove it for the non-integers because that is actually not required for our syllabus. In all the questions that were given, we're always given integer powers. However, you have to remember that this does work for non-integers as well, but even though it works for non-integers, it only gives us one of the solutions. There are other solutions if you use non-integers, but for integers, there's only one solution. So now, let's move on and take a look at some examples where we can use De Moivre's theorem to easily get the answer. Our first one is going to be considering, let's say 1 plus I, and let's say we want to raise 1 plus I to the power of 8. Now, we could expand this using the binomial expansion and then do all of that and then expand and get the final answer, but we could also do it a little smarter and see that we could convert this into the form of r times cosine theta plus I sine theta. Now, in order to do this for this particular one, we can see the size of this complex number is going to be 1 squared plus 1 squared, which is going to be 2 rooted, so root 2. And therefore, I could convert this into root 2 times 1 over root 2 plus 1 over root 2 I, all raised to the power of 8. And here I can see we have root 2 to the power of 8. And then this part right here could be converted into the cosine of pi by 4, cosine of pi by 4. And then this part right here could be converted into I sine of pi by 4. So therefore we have plus I sine of pi by 4. And this has to be raised to the power of 8. Now considering that, we're going to get here root 2 to the power of 8 is going to be equal to 2 to the power of 4, which is going to be equal to, actually, we'll just write that as 2 to the power of 4 for now, and then we'll simplify that later. And then this part right here is cosine of an angle plus I sine of an angle raised to the power of 8, which is going to be this angle times 8 and this angle times 8, which is going to be the cosine of 2 pi plus I times the sine of 2 pi, and simplifying this we can see the sine of 2 pi is going to be 0 and the cosine of 2 pi is going to be 1. So therefore we get 2 to the power of 4, which is 16, times cosine of 2 pi, which I'll directly substitute that as 1, plus I times 0, and therefore the answer is 16. So therefore 1 plus I raised to the power of 8 is 16, and we got it very easily, and we didn't have to use the binomial expansion on 1 plus I to the power of 8. We could of course do it with the binomial expansion, but it's going to be a pain because we're going to have 1 to the power of 8, we're going to have I to the power of 8, and then we're going to have 8 choose 1 times 1 to the power of 7 times I to the power of 1, and so on and so forth. We can have i's, I squares, I cubes, I to the power of 4s. It's going to be a big mess, but instead we can use this method to simply get our answer. Now I recommend you try your own with some things like this. You could of course try something like, let's say 3 minus 4i raised to the power of, let's say, 6 or something, and here you would have to convert this into some kind of angular form. We know if you have 3 and 4, then the total size is going to be 5, since 3 squared plus 4 squared is going to be 9 plus 16, which is 25. Take the square root, you get 5, and therefore we could write this as 5 times the cosine of an angle plus I sine of the angle. So here we can have 3 divided by 5 minus 4 divided by 5 I, and then we have some kind of triangle with 3 divided by 5 as one of the side lengths and 4 divided by 5 is the other one. We'd raise that to the power of 6. We'd raise the whole thing to the power of 6. We'd get 5 to the power of 6 on the front, and then this angle multiplied by 6, and then we'd have to find that angle and then resubstitute, and then finally we'd get our answer. So I recommend you try things like this. You could also of course try some things that are easier to solve, like for example 1 plus root 3i or something like that, which here you can see if we take a 2 out, we're going to get half here and root 3 over 2 here, which, as you know, this is the cosine of 60 degrees and this is the sine of 60 degrees and things like that. In the exam as well, you will most likely be given things like this to solve and not complicated things like this. However, it is not impossible to solve this thing on paper like we would do in an exam. So I recommend that you yourself try doing things like this. For example, you could try and do let's say to the power of 11 or something like this. Try and do this and see what kind of answers you get. So that's going to be all for this video. It's quite short, I know, but that's all we really need to cover for De Moivre's theorem. So that's going to be all for De Moivre's theorem, and that's also going to be all for complex numbers. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching. Click this video for the next lesson, and goodbye.